Okay, we'll get started. Did I post the new homework?
Yes.
Okay, good. All right, good. Yeah. So, fill a particle in the box. You should be able to calculate starting today. Actually starting yesterday, last class. All ready to go. We're going to study particle in the box for the rest of the week, and then what we're going to do is move to what's called the harmonic oscillator, which is the quantum mechanical slinky once we get to Valentine's Day. Hold on to them. I'll bring in my own slinky. They'll be useful as like a little toy. One, to lessen your trauma in this class, and two, to help engage your our discussion about springs, or treat chemical bonds with springs, and slinkies are actually a very useful representation of that. Thank you all. You guys, out of any class that I have, donated more money as students to Dino's fund than any other class I teach. So thank you all. I think there's about 10 of you that have submitted money already. So thank you for that. We're at $737.50 today. So Dino's going to get a check for $3,600 after fees and stuff, assuming no one else donates. So thank you all for that. I would like it to be 4,000 because I'd like to donate another $100. Got to get it to 4,000 first, but that's not your responsibility. You guys, I mean, I'm sure Dino actually will be somewhat upset that you're spending money on this. When I told him that I started to GoFundMe for him, he's like, I think the money's more important to you guys than it is to me. And I told him he's full of shit. And he's going to get his damn check whether he likes it or not. Okay. Let's go back to where we were. I'm going to just kind of talk about some odds and ends and some properties of our particle in a box, and just start to get a sense of why it's useful and applicable. Some kind of exploratory things that we'll do that we won't really do rigorously, but we'll just look at them. But what I want to study, what we looked at last class, was measuring statistics. We used our particle in the box to start thinking about position, means and standard deviations. And we came up with a nice formula that basically, if we have a wave function psi for our system, we can repeat the idea that we have in statistics, which is that the average observable, the average value of some observable for a statistical system, say your grade distribution, is just an integral of that observable times that variable for the observable times the probability distribution, your grade distribution. So if I wanted to calculate an average grade, I could average the grades by taking x, where x is the grade, times the grade distribution. Integrate, and that would give me the mean of that distribution. So this is exactly the same kind of math that you're doing in regular statistics, where you're taking averages of numbers. You sum a bunch of numbers and divide by the number of observations. This is exactly the same calculation, but it's over a continuum, right? We have to integrate instead of sum. We have an infinite number of samples that you have to sum over, and so we have an integral. Okay, so you've seen this before, just not maybe not how things. And so we just repeat the same idea, but we have this special structure where we stick the operator in the middle of the two wave functions. And that comes from converting between vectors and wave functions and integrals. Those two representations we've looked at for wave functions. It turns out that when you're doing vectors, you multiply, you put the operator in between the states. And of course, what does this give you? If these were vectors, if I was a vector, O is a matrix. Remember, like that's that, our spin boxes or deflection boxes. They're matrices. We have a matrix times an operating on a vector. That gives us a vector back, right? That's all matrices do, is they take one vector to another one. So the output of O psi is a vector. And so that's some new vector or the same, hence, times another vector. So this ends up just looking like a dot product in vectors. And dot product of vectors gives you a number, right? Just like an integral, right? An integral, you take in some functions, you integrate over some space, and it spits a number out. Right? So that's just kind of how the math works out. And so we just refer to it. But as we saw, though, with the particle in a box, everything is real. You got a real wave function, real energies, every real box. There's no imaginary numbers anymore. So in some sense, this structure doesn't really matter. for this per position, because X is just a variable, we can factor it out, we can move it around. We're going to see an example where we need to maintain the structure in the integral, where the order of the operator and the wave functions matters. Right? For X, it doesn't, right? I can put X here, I can put X here. Algebraically, they're commutative, right? If X and sine are commutative, I can multiply them into order. We're going to see an example today where that doesn't work. Careful with that. That's why I emphasize this order of operations. Right, and so we did this for X, and we saw that the average position for the particle in a box, regardless of what the energy it's at, is zero. And it just sits in the middle of the box. Right, so what that means is that it's equally on the left as it is on the right. We know it's delocalized, right, spread out over a wide region, but on average doesn't have any bias left or right. The more interesting thing was the variance of X, right? In some sense, the square of the standard deviation, right? And what we saw for X squared is that X squared gives you something that doesn't have any dependence on n, and then it's modulated by this term that's 1 over n squared. And so we can think a little bit about this number. So this is the variance, right? This gives you some sense of the spread of the distribution. How often it is, in some of the larger the variance is, the further it is on average away from the center. The bigger the variance, the further away it is on average. And it's L squared over 3 if n is 1 or n is infinity, right? So what happens is, as n gets smaller, as n is 1 and it starts to grow, the variance gets larger, right? Because this n makes this number smaller. So as n grows, you're subtracting a smaller number. So that means the variance is getting bigger as n grows. And we showed that, I kind of showed that kind of qualitatively with plots. At n equals 1, we have a wave function that kind of looks just like a couple humps. And so the variance of this system is mostly near the edge, near the center of the box, right? Kind of like most things are kind of in this first half, the center half of the box. But as we start to increase n and we increase the energy of the system, increasing the frequency of the wave, what we find is that the wave continues to push out, the probability continues to push out further and further near the edge of the box. And what we find at large n is basically distribution that looks like the particle can be anywhere in the box, right? It's an equal probability everywhere, a square potential like this, which is what we have for a free particle, right? Free particle has no bias on any spot whatsoever, but when it's confined, it does, except when you bring n very large, and it can just basically be everywhere. So the interesting kind of result from this measurement is that, yes, it's on average in the middle of the box, but as the energy grows, the particle tends to sit at the edges of the box more often than not. Right? It starts to push out near the edges. And again, that's not all that much different from, say, an ideal gas. Ideal gases do precisely the same thing. They're constantly hitting the edge of the box, and the pressure they exert on the box, surface of the box, is exactly the same pressure they exert in the middle. So we would expect them to be out on the edges of the box as much as possible, because that's what we observe in an ideal gas. Okay, so in the homework, you actually look at this a little more carefully. You look at the particle in the box approximation for the problem for a macroscopic particle, meaning that you have a nitrogen atom with enough energy to call it 300 Kelvin. You look at, put it in a normal size box, and you'll realize that a nitrogen molecule at atmospheric conditions is represented by a particle with very, very large n. And so its wave function looks like this. And what you'll observe is that the fringes, right, these peaks of probability that you see here, the fringes are so small, the gap between the fringes is so small, the wavelength is so slow, that we can just basically neglect it. Which is why we don't care about the wavelength behavior of molecules when we talk about gases, because their wavelength is completely and utterly negligible. So I'll have you guys explore that a little bit in the map from the homework. Okay, so the other thing that we looked at a couple of lectures ago, besides position, was momentum. And I want to look at the momentum of the particle. And we're going to actually come up with a really, really interesting formula by looking at position and momentum and combining the two results. We're going to come up with a really interesting formula that's universal called the Heisenberg uncertainty principle. We'll look at that next. So let's continue on for now. So what I want to do now is I want to think about momentum. Right? And we haven't thought about momentum in a while. Okay, so let me remind you what momentum looks like. Classically, momentum is a vector, which is the mass of the object times the velocity. And I showed you, I argued that velocity is not a very useful number for us. It's not sort of what momentum is. And what we show is that in quantum mechanics, we can promote this to an operator, which is minus IH bar times the derivative with respect to R, the space, where R is a vector, X, Y, and Z. So it's some spatial vector, right? So we can take that in 1D because we're in a 1D particle in a box and just say that the momentum in the X direction is minus IH bar d by dx. So in order to measure the momentum of our object, we need to take the derivative of the wave function. Right? This is where moving operators around in your integral when you make measurements doesn't work, because here we have to take a derivative of an object. And if this operator is in between two wave functions, psi star, p, psi, I'll write it in a second, we got to make sure that this operates on the correct thing. Okay, so we can't just move it wherever we want like we could position. Okay? So the rule was that the average value of the momentum is the integral over the box of the wave function complex conjugate times the operator applied to the wave function dx. Okay. So let's look at that. We get a factor of 2 over L from the psi squared. That's our normalization. Integral from 0 to L of sine n pi over Lx. And then we have this operator minus IH bar times the derivative. And the operator operates on the thing to the right of it. Okay, so we're going to take a derivative of the wave function, which is sine n pi over Lx. Right? I've already factored out the normalization constant, dx. Okay, so we have to first evaluate, before we do any integral, we have to evaluate this derivative. Of course, the derivative of sine is cosine, very easy, not too complicated. So we have a factor of 2 over L. Okay, I'm going to factor out the minus IH bar. Okay, and now what we have is an integral of 0 times L times sine n pi over L times x. And now we have to take a derivative of that sine, okay, which is cosine. And then with the chain rule, we get an additional n pi over L. So I'll put that over here. And we get cosine n pi over L x dx. But we have to integrate a sine cosine to do this. Now we could go do U substitution, look up a nice trig identity for this, simplify the integral, do all that. We don't have to do any of that junk, because we can, again, use symmetry to our advantage. Let's go back one more time when we looked at the x integral, and let's just make the same argument we did before. When we measure x, we're taking an integral of a sine squared times an x. And so we can think about that integral of a product of the linear function times sine squared. So sine squared is even, x is odd, so the product is odd. And if we're integrating over a box that's symmetric, meaning that we have box, the part of the system is like mirror plane by x equals 0, this whole thing is going to be odd overall across the integral, and the integral is 0. All the negative side less than x less than 0 gets accumulated negative and then is compensated by the positive integral on the other side of it. Right? So that's what that happens with even and odd functions. And we have an even and an odd function here. Sine is odd, cosine is even about x. Right? We can just kind of, I'll just to convince you of that. So this is odd, right? Because sine looks like this around x equals 0. And this is even, right? Because cosine looks like that. Okay, so the net function is odd. Okay, so the integral across the box has to be 0. Don't have to do any math. Well, I can plot it. Really, really nice argument. So what the hell does it mean that the momentum on average is 0? Because what do we know? The system always has energy. Right? Every state has some energy, h squared, n squared over 8ml squared. N can never be 0, so n, the lowest level of n is 1. So these particles always have energy. The energy is composed of its kinetic energy, which is the square of the momentum. Therefore, this system always has momentum. But I just said its average is 0. Okay, so what's the problem here? Well, it's just like position. The average position is 0, but that doesn't mean that it's just always sitting in the middle of the box. It has a distribution. So what does it mean for momentum to be 0 on average? Well, momentum is a vector. Momentum has a magnitude, but it also has a direction. And what momentum equals 0 means is that it's going to be moving to the left just as much as it's moving to the right. So there's nothing, it's not actually saying anything about the actual momentum of the object. It's saying something about the directionality of it, which is that there's no preference for it to be moving left or right. It's that easy. So we'll have to again think, well, if it doesn't have no momentum, what is momentum squared, right? This is where you can see we're taking the average of a square is important, because here we show that with direction, you go negative as much as you go positive, and so the net is 0. It doesn't tell us anything about the motion except that the box is unbiased in its directions. Right? It's not like one side is better than the other. And so p squared is going to teach us something more useful about the actual motion of the system, and hence the kinetic energy. So this again is saying that leftward motion is equivalent to rightward motion. Right, so we could say left motion is minus p, and this is plus p. So they're the same. Right, so not very interesting, but it is an important observation that, again, that should justify that, again, there is no left and right are just arbitrary instructions that we create. It doesn't really matter. All right, so now we have to ask p squared, right? What is p squared? All right, well, we can go do the integral. What is that integral? Let's just look at that integral and then we'll solve it a different way. I'm not going to evaluate. Let's just work through it. All right, so this is the integral of psi squared of p operating on p operating on psi. X, right? So anytime you see a square of an operator, that means you're doing it twice. Right? So I'm just going to say that any operator to the nth power means operating n times. Okay, so we're going to operate twice. We have our PP operator. The other class had a good kick out of that, I'll tell you that. All right, I'm not going to factor in the psi yet, but let's just work out PP. All right, so that's going to be minus IH bar d by dx of minus IH bar d by dx of psi dx. Okay, so let's clean out the numbers.
Right, we have minus I squared. We have H bar squared on the outside. And then what we're left with is psi star, integrating from 0 to L, times the derivative of psi, which is the second derivative. Dx. Okay, we can go ahead and evaluate that. I squared is minus 1. Minus 1 squared is 1. So this is, let's see, it's a little confusing. So this goes away. We have I squared, so this is a minus sign. So we have equal to, no, wait, hold on a second. I squared minus 1. Yeah, that's right. Minus H bar squared. We get a factor of 2 over L from the wave functions. And we got sine n pi x over L. And then we have to take the derivative of sine twice. That gives us a sine back times the negative. I remember sine gives you cosine, and derivative of cosine is minus sine. We're going to get another negative sine and sine back. And then from the chain rule, we get n pi over L squared. Right? And this minus sign gets canceled. And we're left with the integral of sine squared n pi x over L dx. All right, this is a non-zero number, right? We've already calculated something that looks like sine squared. All right, we know this is non-zero. Okay, let me show you an easier way to calculate this. All right, we can certainly do this integral and get the right answer. We know that this ends up being n pi over 2. Is that right? Yeah, it's a number. Or is it 2 over n pi? Why not? These n's are going to cancel out. We get some h bars, we got some l's, you got a bunch of junk here. We know it's going to kind of have these terms in the end. Here's another trick. The kinetic energy, remember that the kinetic energy of our particle is equal to the momentum squared over 2m. Right? That was our definition of kinetic energy, p squared over 2m. Sorry, I have to square that. Okay, so that means that the average value of p squared is equal to 2m times the average value of the kinetic energy. Yeah, I'm sorry. Oh, I'm sorry. I apologize. Is that better? All right, so the momentum is related to the kinetic energy. We have a formula for the kinetic energy already. Let me show you what it is. The kinetic energy is the energy of the system, h squared n squared over 8ml squared. So all we have to do is multiply this by 2m and we have the answer. So that means that p squared, it'd be a hat, is 2m times h squared n squared over 8ml squared, which is h squared n squared over 4l squared. Okay. So we can say that the uncertainty, the standard deviation in the momentum, this is the standard deviation, which we showed is the square root of the variance, which is the square root of p squared minus the value p squared. Of course, p is 0. So this is just equal to the square root of the average value of p squared. So the standard deviation of the momentum is just the square root of this result, which is, I'm off by a factor of 4 somewhere. Where am I off by a factor of 4? N pi L. Oh, I see where I'm off by. Okay. So once I convert h to h bar, okay. So we showed that this is going to be n pi h bar over L. So the net momentum, the average momentum is zero, meaning that it may be moving, it may not be moving, but it's moving left and right without any preference. And the standard deviation of that distribution of momentum has a non-zero value, which means that, the average is zero. It means that the majority of molecules, the vast majority of molecules are moving. And the average momentum they have at the 67th percentile is n pi h bar over L. Okay, so what does that tell us? That means, again, that as the energy increases, the amount of momentum, like the velocity of the particle increases. Well, the momentum increases. The direction is isotropic. It doesn't matter if we go left or right, but the magnitude is increasing. This is the magnitude of the momentum, if you will. So what we can, in some sense, say is that this looks like the magnitude of the momentum of the object. Okay, so the momentum of our electron in the box is increasing. It's moving faster and faster and faster as we pump energy into it, but it's delocalized in terms of direction, right? It can move left or it can move right. And pi h over L. Okay, but let's look at this number a little bit. See if we can learn something from it. I want to look at a really interesting observation. Okay, what I want to do now is say, ultimately, what I'm trying to do is to characterize the state of my particle in the box by its position and momentum. That's what I've done. I've done two experiments that have means of zero. Right? The average position is in the middle. There's no preference whether it's moving left or right. And I have standard deviations to both of my measurements. Right? The uncertainty of my momentum measurement is n pi h over L, and then I've got that complicated formula of L and N for position. So I'm an experimentalist, and I want to think now, what is my total uncertainty for my state? Right? I have a particle I've localized at some energy. It's bouncing in my box. I want to make a measurement of it. What's the best I can do? How well can I really know the system? All right, so what I want to think about is the total uncertainty in X and P, right, which is effectively position and momentum, or sorry, and velocity for a particle in a box. Right? And so we have two measurements. I'll just repeat what I just said, two measurements. We're in lab. We measure X. The average value of X is 0. And the variance of X, let me repeat the number. Was L squared over 3 minus, let me get the rest of it really quickly. Let me just peek it. L squared over 2n squared pi. All right, so that's the measurement we make. And then in P, we make a P measurement, and we find that the average position is 0, or the average momentum is 0, but the average magnitude, just the variance of it, is n squared h bar squared I squared over L squared. Okay. So what we see kind of is we have a measurement of our box. Right? And here's X equals 0 in the middle of our box. right? And what we observe statistically looks kind of like this. We have a mean right at the center of the box, right? And then they have a width that's dependent on n. We have some width. So the distribution of the values that I would measure would look kind of like this. And maybe this one's narrower than the other one. It's not clear. Right? These are what our measurements would look like in the lab. Right? And the idea is that the center position is the average position, and the width of this distribution is the standard deviation. So the question is, what's my total uncertainty, right? So I've got two components of my uncertainty, the position and the momentum. Right? What's the uncertainty of the total measurement? All right. So what we can write is what we can consider is the total standard deviation, which is the worst case scenario, which is I take the uncertainty of x and I multiply it by p. The total uncertainty of my calculation, assuming x and p are independent of each other, is going to be the standard deviations multiplied together. Right? And what we find from this map, I'm not going to walk through the math, but what we get instead is h bar over 2 times pi squared n squared over 3 minus 2 to the square root power. Okay, so what does this tell me? What it tells me is that as n increases, my certainty about the position and momentum decreases. Why is that? Well, remember, as momentum increases, I'm increasing the energy, right? Energy is all kinetic. So as momentum goes up, energy goes up. So as energy goes up, n increases, right? And this says that my total uncertainty of my measurement, which is intrinsic to the experiment. No, there's nothing about the actual measurement device here, right? There's no systematic error in the device yet. I'm assuming that my instrument is perfectly calibrated and has no error. What this is telling me is that this measurement of measuring position and momentum of this electron in this box is inherently error-filled. And that error gets worse as energy increases. That seems somewhat counterintuitive. Let me explain why I think that's counterintuitive. So what this is saying is that my total error increases as energy increases. But in some sense, we had a better understanding of what the electron was doing at high energy. Let's go back again and look at that. Right, remember that position, right? In some sense, from our point of view, at high end, that kind of idea that the probability the electron can be anywhere, that would be kind of in some sense an ideal scenario for us. Because then we don't have to really worry about these fringes and things like that, right? We just know the electron is kind of evenly distributed about the box. So from our point of view, that distribution like this makes a lot of sense. In fact, it brings a little bit of comfort, right? Instead of thinking about where the electron might be, excuse me, where the electron is at low energy and it's got this wave-like pattern, which is very non-classical. And there are very clear spots where the electron never is, and there's very clear spots where the electron likes to hang out. That seems very that seems more confusing, but in fact, it's much more localized, right? Because what I can say here is that even though the electron has this weird distribution of positions, I can know for a certainty, for a fact, that it's going to be at kind of these little middle regions right there, right? It is localized in some sense. It's delocalized over the box, but the fringe region is very, very clear. There's some very clear place where that electron shows up. I really can't say that about these high-end ones, right? I just know that it's everywhere. And the argument here is that in terms of error and in terms of interpretation of your experiment, we're losing information about the electron as we increase n. Okay, where it's becoming more classical, But what we're really losing is any sort of knowledge about where the electron is localized at all. Okay, so when we combine X and P together, that's the clear thing, is that as energy increases, we're losing more and more information about the state of the electron, right, when we measure. This leads to an important point. This isn't anything to do with the particle in a box in particular. In fact, what we'll show is actually the particle in a box is, in some sense, one of the worst situations for this, that this error is actually a lot higher than it could be. And the rule I want to teach you today is a consequence of this. It's called the Heisenberg uncertainty principle. Let me spell his name right. So Heisenberg was Werner Heisenberg was a very famous Jewish scientist in the 1920s and 1930s, very, very intelligent. He was also a member of the Nazi Party, ironically. Has a very complicated history because of this, or for being one of the Jews that chose not to escape Germany, but instead joined the Nazi Party and was the head. Heisenberg was the head of the German Manhattan Project, which failed miserably. Thank God. When World War I ended, or sorry, World War II, ended, and we had Operation Paperclip. You know, if you guys ever heard Operation Paperclip, it's a CIA initiative after the end of World War II to bring in Nazi scientists to run our U.S. labs. That's how we got Wernher von Braun, our rocket scientist who developed the Apollo rocket. He was an ex-Nazi that he created the V-2 rockets that they were aiming towards Britain, and we brought him over to do work for us. And Heisenberg was one of those guys that was considered, and his Nazi connections were so problematic they didn't let him come over. Heisenberg kind of disappeared in obscurity in Germany after World War II because of his ironic commitment to the Nazi Party as a Jew. So actually, the actual German Nazis got better treatment than he did because I guess they expected Aryans to be racist, but not the Jews themselves. So very interesting story, but Heisenberg is an essential part of this story. And what he says is he proves very generally. He shows us that for any system, any quantum mechanical system at all, that the combination of the standard deviation of X and P, right, that total error of this measurement always is at least h bar over 2 for all systems. So what this is saying, right? So let's think a little bit about what this means in practice. Right? So it doesn't matter. Well, we can go back and look at the particle in a box really quickly and compare. If we set n to be 1, here, we have pi squared over 3 minus 2 square root. That's a number larger than 1. And so that means we have a large number larger than 1 times h bar over 2. So for the particle in the box, it's actually worse than the Heisenberg uncertainty principle. Right? Because for particle in the box, it's h bar over 2 times something. The error is it's not even perfect. We'll see a system later on that actually satisfies this equation exactly. Right? So you can construct a system that has a minimal error, but you can never go any lower than this, right? So what this is saying now is that, and the real consequence of this is that the more we know position, the less we know momentum. Right, let me show you an example. All right, so let's look at some limiting cases for this, all right? And this ends up being a really of practical concern in the physics and the chemistry community when you're working at quantum mechanical levels, is knowing that there's some inherent uncertainty into let's say, for instance, you want to create a particle that you want to collide with something. You want to excite an electron at some momentum or a photon or something like that. You have a trade-off between knowing its momentum and knowing its position. We could define its momentum exactly, but then we don't know where it is. It's just a wave. Or we could define it to be a particle, which has a really defined position, and then we know nothing about its momentum or its energy. Right? So we have to be careful about that. So let's think a little bit about this a little bit. All right, so let's look at some limiting cases. What if we assume that delta x is 0? We have a localized particle. All right, what does the wave function for this look like in position? So we have this x, and what we're saying is that at some position x sub I, we have a wave function that basically is a little peak, right? This is phi. X sub I, right? It's just a little delta, what we call a delta function. The delta function. It's just a little one, it's 0 everywhere except for that point. Right? It turns out that, I know this sounds really weird, and we won't go into the details of why it is. This is a continuous differentiable function, so it's actually a valid wave function. It's just a point in space, but it turns out you can integrate this, you can take a derivative of it, you can do all sorts of stuff. That's pretty cool. And then what you ask is, what's the momentum of this state? All right, well, let's think about it, right? So what is the uncertainty? What is delta x or sigma delta x, sigma x? The standard deviation of the state is 0. So sigma x is 0. We've localized it exactly the same position, which means by definition, sigma p is infinite. Okay, so what would that look like on a momentum plot? Well, on a momentum plot, we have a bunch of momenta, P0, P1, P2, dot, 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 dot. Every single one of them is equally likely. Right? So our wave function in terms of P, it's just a straight line. So, okay. So we know nothing about its momentum if we have an exact. Right. So another way to write this, it turns out, is that in order to construct this wave function from a bunch of sines, right? Remember, wave functions are just sine waves. There ain't no sine wave that looks like that, right? So how do you take a bunch of sine waves and add them together to get a single point? All right, it's very tricky, but it turns out you have to take an infinite sum of sine waves. Right, so let me write that really quickly. Let's talk about that argument. It's really, I think, kind of important. If you treat psi of x, or the wave function of the system, of whatever this system is, as a sum from I equals 1 to whatever, infinity, of each of the different wave each of the particle in the box states. Let me write them differently than that. Let's just calculate them out. This is 2 over L to the 1/2 power sine I pi x. Let's sum over n instead, because we've been using n. Sine n pi x over L. Right? So we just sum over a bunch of wave functions. We're going to construct our system, our wave function for this localized state, out of a superposition of our basis states, which are energy wave functions of this system. Right? And the question, of course, is how many of these do I need? How many does my wave function, how many states do I need to add together to get this? And the answer is infinite. Is that this needs infinite energy states are required for a localized particle, a fully localized particle. Right? I really mean by infinite. right? Because this function is made up of a bunch of sine waves, right? So the wave function is just sine pi x and 2 pi x and 3 pi x and 4 pi x. And it's all the states together. Different levels of intensity. Some states might not be populated at all. The states might be zero. Some might be large. Some might be small. It depends. But the point is that each one of these brings an energy, right? These are the wave functions of fixed energy. Each one gives you n squared, h squared over 8ml squared. And so a state that's perfectly localized is a state that is represented by all possible energies. Right? What that means is that there is no information. The only way to localize a particle is to lose all information about its energy. It's not surprising that that's impossible to do. Right? This is just a limiting case. But what it says is that we have to basically construct particles in order to have it perfectly localized. We would need to include infinity energy into it. Okay, so basically it's impossible to do this. Right? Anytime we reach an infinity, we know we've broken things. All right, so what this says is that it's impossible to perfectly localize. All right, let's think about the other way, where you have a state of known momentum. What are the positions? We've already looked at this. So let me flip it, and let's go back a couple pages, and look at our wave functions for this system. Each of these wave functions, sine and pi x, they have a fixed energy. Energy is dependent. A fixed energy, right, means that you have a fixed magnitude of your momentum. Okay? And so that means that if we have fixed energy, a state of fixed energy has a fixed momentum magnitude. It's moving at some net momentum. Right? We know that the direction is isotropic. But the actual magnitude, the velocity of the system, if you will, is determined by the energy of the state. So these are states of localized momentum, right? These are states that have a fixed energy and therefore have a fixed momentum. And in position, they're completely delocalized, right? They're sine waves. Okay, so you already see this. You've already seen this idea that when we zoom in on the energy, pick a single energy, we lose all information about the position. Right? It's perfectly delocalized. So you've already seen half of this argument. Right? This is what I mean when I talk about momentum and position being conjugate variables. It means that in some sense, they're both related to each other statistically. Knowing momentum means you lose information about position and vice versa. They're connected in some unique way. And that's why we always consider them, and that's the reason why physics is defined with position and momentum, because they have this intrinsic concept in them, that they're correlated to each other, and we're seeing that bear itself out in quantum mechanics. Right? Where if we know one, we don't know the other, and vice versa. All right, so we'll see that time and time again, and I'll give you some more examples and some ideas of where the consequences of this idea is. How am I doing? Okay. Okay, so I'm going to stop talking about math for a second. I want to show you some simulations of a particle in a box. So I think quantum mechanics, because sometimes it's easier just to see these things happen in a box. So some simulation. So let's go look at one. I don't know how well this is going to work, but we'll give it a shot. So what I have here, this is a infinite square well, right? Our box, our infinite box, and I can set the energy of my system with this line here. And what you're plotting here is, as you can see, is psi squared, right? So if I bring the energy all the way down, you can see that as the energy increases in the box, my wavelength decreases, my frequency increases, right? And so as I increase the energy, I get more and more fringes I don't think I used this term last class. I'm just going to remind you. Let's go over to that. Let me go back to my conversation really quickly. I just want to use a quick term for you. When we were talking about these wave functions squared, I called these little peaks in the probability fringes. Talked about fringes. I didn't give you the name for the points at which there's no probability. The opposite of a fringe. Right? These are called nodes. So let me call it. These purple points here, where the probability goes to 0, these are called nodes. Okay, so we have fringes and nodes in our wave function. Okay, this is a very classic kind of pattern that you see. Okay? So we have this oscillating series of fringes and nodes as we vary the energy. Right, the important thing to see is that I'm plotting, as you see down here, psi squared. Psi, this is the position representation of the particle system. And it's delocalized across space, right? And the reason why it's delocalized across space is that fixed the energy. Right? That red line determines the energy. It's a fixed energy, therefore the momentum is fixed, and therefore the position is delocalized, and the position is everywhere. As you can, and this is, maybe that starts to think why the uncertainty in our measurements increase with energy, right? The reason why the uncertainty gets bigger is because there's more fringes, and the fringes are now nearer the edges, right? So the particle is spreading out. So even though its behavior as energy increases gets more classical-like if you were like this, you're like, damn, that's a really weird particle, right? It only has 2 fringes that are very broad. But you can say with fairly good certainty where that particle is, right? Whereas that uncertainty increases, the behavior becomes more normal, but our uncertainty is actually increasing as energy. All right, so this is, but here's the thing, not much interesting is going on here. This is just a probability distribution. This is just the result of a 10,000 experiments that you do where you take pictures of the electron and measure where it is. So there's no time dependence, there's no dynamics involved in this, it's just a measurement result. So maybe it's interesting to think about what the system is doing in time. Right? Remember, we're giving it some energy, it has some momentum, and therefore you can kind of say it has a velocity, has a group velocity. This wave is propagating through the box at some time. And we can simulate that. I'm not going to do time-dependent chemistry in this class just yet, but we can look at that. Right? And so what we have here is the time dependence of this wave. Right? And remember and as you can see, all it's doing is oscillating in the box. This is that transverse oscillation that I talked about, the imaginary oscillation of the wave, right, which we neglect in the particle in the box, but remember that the particle is always a complex wave. And the reason why this particle is not in position, not moving back and forth, is because we've created what's called a standing wave in the box. Remember, the whole point of constructing this wave function in this box is that the wavelength of the wave function matches the length of the box. So that when the wave bounces back and forth, the electron bounces back and forth, the ridges and the nodes, the fringes and the nodes all line up with each other, moving forward and back, right? Constructive interference. And so we have a wave that's constructively interfering with itself that causes it to freeze in place, the frozen wave in position. So the wave fringes don't move in this box, because it's in resonance with the box. All the forward-moving propagations are exactly equal to the ones moving backwards. So there's no net motion. So all we see in this state is it just oscillating in a perpendicular direction. Flex. Now let's look at, so that's position. What does the momentum wave function for this look like? Right? And this is what it's a little hard to see. Can you get the light off over there? You know, if you don't mind, let's do one there. Thank you. Right, and so let's look at this behavior. Right, as you can see, the momentum peaks at particular locations, and the location in which the highest peak is n pi h over L. Right, remember that the average momentum is 0. We see that exactly, right? When the left peak is up, the other peak is down on the other side, so they cancel each other out. So the net momentum in the system is 0. We saw that the wave doesn't move at all. But the momentum structure of this system is localized because the system is delocalized, right? The position's delocalized, so the momentum has to be localized at some position or some momentum, and there you can see it. There are two peaks of that momentum, right? And those correspond to the forward traveling momentum at this energy and the other one to the reverse travel. They're both the same size and they're 180 degrees out of phase because they all have to cancel out when you average them. Okay. Right. If I change the energy of this system, we'll see that the location of this peak changes. As I bring it closer together, oops, that was a little scary. As I bring the energy down, you can see it's oscillating more slowly because the energy is low. The frequency of the oscillation is function of the energy. And as you can see, both of the peaks, there's two peaks here, but they're adding together. Kind of looks like one. Okay. So as I start to increase the energy, you'll see that the oscillation speed starts to increase. And then the two components start to split out. Right? So what's happening is now I always have two momenta. There's one going this way and one going this way. It has to be. And what's happening is that the standard deviation of the momentum as I increase the energy is increasing. Right? And so it spreads the wave function of the momentum out. And you can see it's a little delocalized, but it kind of looks like just a peak. Right? There's a kind of a little bell curve at that moment, like we expect. Okay, that's the Heisenberg uncertainty principle in action. And again, as I increase the energy, right, it starts to spread out further. We can look at that momentum squared, right? And you can see that once I do that, right, you get fixed positions, and these are the momenta at those two, and they come together as the energy drops to zero. Okay, so delocalized position means localized momentum. Now, let's do something fun. Someone asked this last time, and I think it's a good question. What happens if the box is leaky? Meaning that there's some escape probability. So if we have to they have to be very careful about this because there's a lot of different variables going on here. If we think about this box again, this is not height, but energy, right? It's a potential energy. And so what we're doing is now we're doing a box that has finite. That's right. Well, there's some energy. If you can get the particle enough energy, it might escape. Okay, let's see if we can watch it escape. What we would expect is that if the energy of the particle is way below the escape velocity, the escape energy, that it should look like a particle in the box. It shouldn't look any different. So I'll lower the energy super low. Right, and we see that the wave functions for momentum and position look very similar to what we've seen before. Right, so any particle that has energy deep in this box looks very much like a wave function of a particle in an infinite box. But notice what happens as I start to raise the energy closer to the escape. Right, the momentum increases, which means that the momentum peaks are spreading. We're getting more and more frequency in our positional wave function, the yellow one. But what I want you to notice in particular is that as I start to increase the energy, notice that the wave function doesn't go to zero at the edge of the walls. I'll kind of scroll through it and look at those. Look at the amplitude of the wave function outside of this purple region as I increase the energy. That's the thing I really care about here. Very, very low. I have to get the phase matched properly. Like this. This is a perfectly fine state of the particle in the box, right? The wave function basically goes to zero at the edges. My energy is very low compared to the escape. And now let me jam it up really high. Okay. Now you can see that the last fringes actually propagate into the box a little bit. Okay, so what that means is that there's some probability that this electron is actually in this wall right here. Inside of it. Well, what the hell does that mean? Well, it doesn't really mean anything from our point of view. It just means that the electron is just kind of, the wall is leaky, as I said. The fact that there's some escape probability at some energy And as we approach that, it's getting more and more likely that the electron might just happen to have enough momentum to escape over the barrier. And so some probability gets built up on the tails, meaning that there's some probability that the electron might be found inside the walls. And I could just keep bringing the energy up closer and closer, and you can see, well, we'll go back to that in a second. You see very dramatic, right? So right at the edge, you can see, I don't have the phase match just properly here, but you can see there's quite a bit of amplitude. Now, what happens when I go above the wall? Well, now the particle has no probability of being, basically no probability of being inside the wall, inside the walls. And now there's, because it has enough energy to escape, and the probability density now shifts to outside that region. And as you can see, there's very little probability the electron is there. And the most important thing is that the momenta goes from having two to many, many, many different momenta. So this is what we're doing here, is looking at the change, it turns out, from a particle in the box to what we have up above it, which is a free particle. Right? You can see the response of the box is smoothly disappearing as we approach the edge. And then once we escape it, we have a free particle. And what it looks like is that this particle is just kind of moving, and it's kind of hop skipping over the box. There's some probability that we'll find it in the box, but by and large, it's kind of hopping and skipping over the box. Now, here's the cool idea. What if I make these walls finite in width and put two wells together separated by a narrow wall? That's leaky, a leaky narrow wall. Let's look at that. So let me go ahead, and I don't want to ruin the surprise. We'll do that. Let's look at this one. Okay, so here I have an infinite well that's been truncated into two regions, okay, that are leaky. So let's look at psi squared in this box. Let me bring up the energy high enough. Right? So I think the way that this system is localized is that it initially localizes it. We have to make some argument about where the particle is initially, and I think the idea is that it's over here first. And you can see what's happening, that when you're at low energy, the particle exists primarily in that box. And notice that the momenta are somewhat canted to the left, because what's happening is that there's the particle is feeling, in some sense, a different force against this wall than this one. Because it really doesn't want to go across this wall. It's an infinite potential on the right side. But on the left side, it knows that it has some idea that that's a leaky potential. The wave behavior at that narrow wall is different, and it reflects the wave differently than the right wall does. The right wall is a perfect reflector, but the left wall absorbs and transmits some of that wave as well, because it's a little thin, right? Just like glass does. It's slightly translucent. And so what that does is it biases the momentum towards that direction, because the system is bouncing off the right wall, but sometimes it's getting absorbed by the wall on the left, it's getting bounced by the wall, it could be transmitting through the wall, lots of different possibilities. And so the system biases itself towards the easier path, if you will. It's easier and more likely for it to be over here. Notice what happens as I increase the energy. The electron starts to appear on the other side of the wall. You'll see that there are certain energies that reflect very nicely, right? Right here, for instance, there's very little probability that the electron is on the right side, on the left side, but it's on the right. But if I pick a right energy, you can see now, eventually I get to a certain point where now it prefers to be on the left. And here it prefers to be on the right. And then eventually I get above it, and this isn't exactly perfect. But up here, it should be equally on both sides. Well, there's going to be more probabilities on the right because there's more space on the right than the left. But the important thing is that even though my energy isn't high enough to escape the box, right? If this were like two hills next to each other, two wells of like two valleys, and you've got a hill in the middle that you have to roll a ball over to get it from one side to the other. If I don't put enough energy into the ball to roll it over this hill into this one, right, what does it do? It just rolls right back.
So what I've done with this electron is I've given it a decent amount of energy, but not enough to get over the barrier. And yet the electron still passes through the wall. This is the pure definition of wave property. What this electron is doing is when it hits this wall, it has a choice. In some sense, there's some different pathways. It can reflect, which is what it does on the right wall. It can absorb into the wall. And in fact, we saw that absorption. I'll show you again in a second. And it can also transmit, meaning that somehow some probability escapes the wall as the wall is absorbing that wave. Right? You think about like a blanket, right? You shine some light through a blanket. If it's a really thin, crappy prison blanket, the light comes right through. If it's light, some of it reflects if you have high albedo, reflected blanket. But by and large, most of it passes through. Then as the wall, the blanket gets thicker, right? Output light gets dimmer. Eventually, the blanket's so thick that no light shines through it. Electrons function exactly the same way. Given enough energy and you give it through a thin enough material, the electron will pass through that material. Right, let's look at what happens to this wave in time. That's not very helpful. I want to do a wave packet. Let's see if I can find that for you. Oh yeah, this is the one I want. No. We're close. Okay, well, I'll find one for next class. But what I'll show you in this class is that what we can do is set up a calculation where we localize an electron in this box, its energy, and then we watch its wave function as a function of time. And what we'll see is that the wave function will bounce back and forth across the walls with some reflection, but there's going to be a transmission probability of the wave function passing through this region of the wall ring. And so what we'll see over time is a probability distribution that changes. It's initially here, and then some of it will bounce off the wall and come back, but some of it will transmit through the wall and show up on the other side. That transmission process we call tunneling. Tunneling, right? It's a completely universal process, and electrons are not the only things that tunnel, but hydrogens in particular are notorious to tunnel. You can tunnel a hydrogen through just about anything. Hydrogen you can put on one side of a barrier, and it'll show up on the other one. In fact, the whole process of exchange of a hydrogen between two oxygens, I know some of you might be in advanced orgo right now, modern orgo, learning about enol chemistry. You guys learned about it in PChem last lab. Enol, in the enol form, you have that hydrogen that's being shared between those two oxygens. And you can show that that motion of that hydrogen being shared between those two oxygens is a tunneling process. The electron is not rolling, the hydrogen does not have enough energy to go over the barrier. But the hydrogen is light enough and the barrier is narrow enough that that hydrogen tunnels back and forth between the two oxygens. Right? And it does so at 0 Kelvin, right? With no energy whatsoever. You can put the molecule in its ground state. And the hydrogen is still tunneling between the two oxygens. Lowest possible energy, way down here. And then yet that hydrogen is still moving between those two oxygens as if it were teleporting. We showed this spectroscopically that it does this. Right, and the interesting thing I'll show you, and this is my last comment, is how the hell does a real object propagate itself through a wall? Right? I mean, in fact, how does an atom do? An atom has size, right? It has a mass. It's not like an electron that's just a wave. I mean, it's got a physical mass to it, physical size. How does this physical object end up here, start here, and end up over here? still comes down to its wave properties. And what we're going to see is that when we separate the wave into two components, the real component and the imaginary component, transfers. What we'll see is that the real part of the wave reflects. So the real part of the wave reflects, but the imaginary part of the wave transmits. And so what you get is a desynchronization of your two waves. You have a real wave bouncing back and forth and a complex component that's traveling through the well. And then when you take the square of that, take the absolute magnitude, you lose all that complex information. And what it looks like is that you have a wave propagating back and forth and bouncing and reflecting, and the wave is also transmitting simultaneously. So all of that process comes from the fact that there's a complex component. If it didn't have a complex component, it would never tunnel. It would just reflect. Right? So the fact that there's complexity, imaginary numbers in these wave functions, is proven by the fact that you can watch hydrogens literally move through barriers unimpeded without having enough energy. Okay, so we'll look at that a little bit more next class. And what we'll do next class as well is to talk about spectroscopy. That'll be our next. Okay, have a good one, guys.
It can't be that. I'm just gonna go to the baker's, so I'm assuming my chair, that's the literally like. Where she went, there's two kids. I were machine, it's my birthday, but third mistakes. If I'm remembering correctly. That would.
Kylie, if you're there on Zoom, I have a gift for you, a little mini slinky. Come next